So velocity.
Doing okay?
Yeah, I had to brush my teeth. So, yeah.
Good, that's okay. That's a good thing. That's a good thing. All right. There are a couple of weird little things that happened in this question, right? So let's just do a show of hands. I want you to commit to either the student is right or the student is not so right. Okay? No judgment, just question, just asking. Yes, I think the student is correct. Raise your hand. Put them up high. Believe in it. No, the student is not right. Okay, we got like 50-50. Defend your position. I'm not going to tell you the right answer. That's not how this rolls. Go.
Well,
tell me.
At the end of the graph,
yeah.
A is still on a higher velocity.
Okay.
Which is how much you travel over a certain time. So right now A is traveling further over a certain time, but B is accelerating faster. So that's why it has a higher slope. Steeper slope.
Yes.
That was a lot of information. Did you guys catch that?
Yeah, I agree with that.
I don't know. I mean, sometimes people just use fancy words. I don't know. Say that one more time so that we can really understand it. Because this is weird, right? Keep talking.
So A is at a higher velocity, and velocity is how far you travel over a certain period of time. And right now they both are going the same period of time. But A is traveling faster because it's like, okay, so its velocity is higher. So it means it's going faster. But B is accelerating faster, which makes it so the slope is steeper.
You guys catching what he's saying? So if we look at any point in time, like if we look right here, who's going faster, A or B? A, because A has a higher velocity. Like literally at this time, it's got a higher velocity. Does that make sense? Whereas this one is lower. If we look at a different point, here, who's going faster? A or B? A, right? It's literally a higher velocity. Yeah. So, yeah. Now, when you first looked at this question, your inclination with this whole slope thing, why would you maybe have agreed with that student to start with? The graph is tricky?
It's tricking you. Yeah, it's trying to trick you.
What is so tricky about it? Go ahead, Stella.
Usually it's the displacement. So when the slope is steeper, I don't know.
Yep, keep talking. Yeah. So usually, most of the conversation we've had so far has been a displacement versus time graph, right? And in a displacement versus time graph, the higher the slope, the faster you're going, right? You're moving at a constant speed, just faster or slower. Is that okay so far? This one is in a displacement graph, though. That's why I like this question. That's why I wanted to start with it, to make sure that we're paying really close attention. Go.
If you were to extend time, though, would you see that we would overtake A velocity?
We're assuming that they stay at that constant acceleration, right? If we assume that and we take it out, that's a really good point. If we did, then we could see, right? So A, if we assume it's going to keep going something like this, and B is going to go something like this, and then, whoa, somewhere way out there, for sure. Absolutely. There would be a place where now B is going the same speed as A, right? And then would even go faster and faster and faster. Yeah. Because this one is, as Ben said, accelerating faster. Does that make sense? Yeah. This is good thinking. Okay. You have those charts from yesterday. Do you remember that we started with yesterday, this graph sheet? Does anybody need one? I don't remember. I think you all. Your bright pink sheet means we want to hold on to it forever. Anybody need one? Either I lost it, something terrible happened. This is the thing that we're going to hold on to and put in our notebook and keep forever. So we just kind of started doing this. And I can't even remember what I told you from last time. Except that this was a displacement versus time graph, and I gave you this graph. If I was going to have, Matthew, if I was going to have you come up and act out this graph, what would you do? Sorry, I didn't mean to put you on the spot in a scary situation.
Stay still.
Yeah, absolutely. Because we're saying where your position is, that's perfect. I'm standing here and time just keeps on going, right?
Yeah.
Absolutely. So you're just going to act that out by not going anywhere. All right. So tell me then about the velocity versus time graph. What would it look like? It's on the x-axis, right? Because as he said, we're going to stand still. We're not going anywhere. We're standing still. So let's do it. Let's just draw that out. Here we go. I'm just going to kind of color it in. It's really hard to draw things on the x-axis because, the x-axis is there. So I make them a little bit thicker. Okay. And the way that I have this labeled here, we said, and I think we wrote this yesterday, right, that we're going to look at the slope to find the velocity. The slope was 0. So this box up here is like what we're going to graph. Okay. So the thing we're going to graph is that the slope of the d versus t graph determines, make this a little bit bigger so you can see it maybe a little better, determines the values of the v versus t graph. The slope of the d versus t graph determines the values of the v versus t graph. So the slope over here, you just told me was 0. So the values for the v versus t graph, like the things you would actually plot, are all going to be what? Zeros. So I'm going to say values equals 0. I'm just kind of doing that to remind me of what I'm doing. This is going to be one of those nice pieces that you could refer to when you're doing homework, studying for tests. This is a good thing. Okay. So this is the next step. This is the step that Ben decided to take. Kind of, he was like, I'm just going to forge ahead and I'm going to assume that something's right. Or maybe I learned this in math already. I don't know. Whatever way it was. I've got displacement. I've got velocity. If my velocity changes, what do I call that? Starts with an A. Acceleration. Yes. So I'm going to label this one my acceleration. I'm getting kind of crowded in here. I need to make this bigger, I guess. Versus time. There's some really nice symmetry going on here, friends. D versus T to V versus T. We're going to look at the slope to find V. Going from V to A, we're going to look at the slope to find A. Are you with me there? Boom. It's easy. So we're going to look at the slope. Of the V versus T. Oh, excuse me. I'm just going to say look at the slope to find A versus T. Hey, what's the slope of this? 0. Not very exciting, right? There are 3 levels, so it's going to get more exciting in just a minute. We're doing the easy stuff first, right? Slope equals 0. Anybody want to predict what the acceleration is going to look like? Super unexciting. Help me out. What's it going to look like? 0? Matt said he was standing still, right? If he's standing still, is he accelerating? Nope. Not super fun. Not yet. Just you wait. Just you wait. These are going to be, so the slope of V versus T graph determines the values for A versus T. Again, the slope here is going to be the values here. The values are 0. How are we doing? Are we okay? I want to do something a little bit more exciting. As much fun as that was. Sorry. Did you guys all get that? I didn't want to go too fast. I'm just excited. Because I want to do something more fun than just standing still. I'm going to label this one over here displacement again. And down here we're going to put time. more exciting than standing still? Walking. Take it one step at a time though, right? Get it? The joke. That was kind of funny. I don't know. We're going to walk just at a constant speed. If I'm going to walk at a constant speed, what's the graph going to look like? A straight diagonal line. I love it. Yes, absolutely. So it's going to have some sort of like something like this. Is that kind of what you were implying? Yeah, something like that. Remember the slope of that's going to determine the velocity, right? Okay. Hey, we just know that. The slope of the line is going to determine the velocity. So we're going to say that the slope, I'm not going to write all that stuff down this time. I'm just going to say, oh, by the way, the slope here is, what are some words we can use to describe slope? Constant. Awesome. There's one more that I want. Has to do with which way it's going, this way or this way. In this case, it's positive, right? This one is constant and positive. Going to look at my notes from above. I said up here that the d versus t graph determines the velocities, or the slopes determine the values of v. So if the slope here is constant and positive, tell me about the values for this graph. What are they going to be? So let's write that down. So the values are going to be constant and positive. Oh, we can do that. How do I do that? What's that going to look like? Constant and positive. You doing like some interpretive dance there?
Yeah. So we're going to have a straight line with something more fun.
The values are going to be constant and positive.
Yeah.
Doop, 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 just a straight line. With a slope of what? Oh, by the way. Oh, that's really interesting. Because now I want to look at the slope of this line to get my acceleration graph. If I'm walking in a straight line, see, watch, you ready? Here I go. Is there any acceleration in my motion? There's none. It's just like the buggy, right? It's just going in a straight line. Not very exciting, like more exciting than the before, but not too much. So the slope here, oh, what is the slope here on this one? 0. So tell me about the values for this acceleration versus time graph. It's going to be exactly the same. Again, not super exciting, but wait, there's more. Here we go. So we're going to say the values here. Oh, the value is going to equal 0 because there's nothing exciting going on. There is 0 acceleration. No acceleration happening in either of these situations. I don't know why this is not coloring. There we go. That's better. How are we doing, team? So far, so good? Making sense? Where's my... Can I? There we go. Okay. All right. So, one more time. This one's not exciting, right? That's just something sitting still. This one here was like the buggy, right? We graphed this. Then we did another lab after we did the buggy lab that we just finished yesterday, and it made a curve. What was going on in that case? Say again?
Accelerating.
It was accelerating, right? That ball was going down the ramp, and as it went down the ramp, the velocity kept getting faster and faster, or the speed kept getting faster and faster and faster. Yeah, that's even more exciting. So let's do that one. We're going to write that down here. I don't know. Let's do purple because it is, my freshmen were telling me, is it true that Gordon says that Friday is actually just called Bolt Day? Is that true? That's what I've been learning. So yeah, I learn these things slowly but surely. It is. So we'll do displacement and time. And now when you graphed that, or when you graph it, because you may not have done that since it's not due until Monday, some of you asked me yesterday when you were graphing, you're like, can I just, draw a best fit line? And what did I say? I said, no, don't do that. Why? Because it's a curve, and there's actually a fancy name for it. It starts with a P. My math people love it. It's a parabola. Yeah, and if you're like, I don't remember what a parabola looks like, that's half of a parabola right there. Boom. But, it's parabolic curve, so that's cool. We kind of drew this out yesterday, didn't we? Did we talk about this when we showed the little... Yeah, I feel like we did this. So I'm going to zoom this in, because I know you can't do that on your paper, but I just want to make sure you can see it. So we can look at the slope. Remember we did this before? We did like that little tangent line thing. I'm going to do it in highlighter, because then you can see it better. So there's one like this, and there's one like this, and there's one like this. And so tell me about that slope, because in the arrows, remember, arrows are going to have those slopes. So tell me about the slope in this graph. It gets steeper. It's not constant, right? And in this case, we've got it going up. So we're increasing. Every single time, it's going up. So we got increasing. And in this case, it's always positive. So now, at your tables, see if you can draw a velocity versus time graph. It's not the slope now, it's the values are increasing and positive. Try it out, talk to your neighbor, have a conversation. We love pencil just in case we make a mistake, but maybe you got it. What is it going to look like? The values are increasing and positive.
Is that a curve? Yeah.
I feel like, don't let her take credit for that.
I just don't like when I started interrupting.
Erasable is like, yeah. Yay for new technology, right? The erasable pens that we had when I was a kid were like the erasing, it was like it erased, it just got lighter. It's like, this is not really good. What is the velocity versus time graph going to look like? Patience, did you guys get something? Nope. Can you help me? Can we figure it out together? Awesome. Okay. So here the slope is increasing and positive. I want you to think about so let me plot a point. Let's say at this time, the velocity's here. I want them to be positive, right? So they're always going to be up here because this is the positive part of velocity. So if I go over here, where does it need to be? If it's increasing, if the velocity is increasing, where are we going to go? Up. Yeah. It's going to go over a little bit more, and it's going to go up. And we go a little bit more. It's going to go up. You with me there? Yeah. It's going to be a what? A line. Look at that. Pretty. And now we're going to take it one step further. You ready? The slope of this line, of this graph, I should say, is what and what? The slope. And constant, yeah? So we're going to write down positive and constant here. Any inclination based on what we've done so far? What's going to go in this little box thing? What goes in the box? Is it slope stuff or is it the values, right? So the values for the acceleration versus time graph are going to be what and what? Constant and positive. Is that okay? So then talk to your table mates. How are you going to make that graph? Constant and positive. You can. That would be like the negative. Yeah. So our calculus friends can tell us then how you can get backwards to get there.
negative acceleration.
And we're gonna talk about what that is, and we are going to do a little bit a lot. Does that make sense? Yeah, yeah. So we'll get there on Monday. Well, kind of on Monday.
What would be like deceleration?
Yes, yes, and that's just called negative acceleration also. We will, yeah, we'll talk about it. We're gonna like parse out all of the negatives and positives, because there are lots of different ways to do it. Yeah, we'll get there. What does our graph look like? What's it look like, Josie? Idea or no? Like which one? Like this one? Okay, well let me ask that. This one says values equal 0. Does this one say that values equal 0? It doesn't. So how can we process that then? These values are constant, but they're all what? Positive. So where's that line going to be? You got it. You got it. That's why we use pencil or erasable pen, right? Yay. Yay for being able to make mistakes and loving that, right? How's it going? Are we okay? Is this making sense? Oh, there are 2 more things that I want to write down. Because I forgot. Did you notice that there are 2 bubbles that aren't filled in? The little like thinking bubbles? One of them we already know the answer to. This one's the one that we did when we rolled the ball in the hallway. Do you remember how we got from the displacement graph to the velocity values? We used the slope, right? And we calculated the slope. And the slope was rise over run, right? And oh my goodness, it's really loud. Oh, can you close that door for me? Thank you so much. I always forget that it gets really loud. The velocity is going to be the displacement over the time. Yeah? The reason I like that, we already know that one, but then there's another bubble over here. That bubble is going to tell us how to get to acceleration. We don't know that. We're doing it right now because you're figuring it out right now. You don't need me to tell you an equation. You can figure it out. Because remember, I used to write that D, because I didn't usually write that D, did I? I usually wrote that as a delta X, a change in the position, right? So really, that's the change in Y over the change in X. What would be the change in Y over the change in X here? What's the Y values in this one? Velocity. The change in velocity over time. And the change in velocity over time is the boom. Eh?
Yeah.
That's all it is. That's all it is. Oops, I want to make that purple. Come on. Change in velocity over time. That's what we're going to do on Monday. We're going to plug numbers in and figure out exactly how to do that. But right now, we're just going to know that that's true. The slope, boom.
If you put velocity in that equation right there, those are 2 different times, correct?
So
if you put
keep talking.
Velocity as d over t divided by t, those are 2 separate times, right?
Right. So this is actually a time span.
Yeah.
Yes. So yes and no.
You can't simplify that though if you put those. You try to write it out like that.
So yes and no. I'm going to totally hedge that. Kind of. In that, and again, we'll get to a lot of this on Monday, but if you have displacement over time, that's going to be meters per second.
Yes.
You're going to divide that by seconds. So that's going to go down to meters per second squared, which is the unit for acceleration. So literally, when you're speeding up, you are increasing your meters per second. Does that make sense? So you kind of do that, but you would never like literally plug those numbers in. It doesn't quite work that way. But I'll give you a bunch of equations to make it all happy on Monday. I just don't want to do that today. How are we doing? Are we okay? Okay. So now I want to actually use this because, I mean, like it's nice to fill in a chart, but, you know, it's better to actually do something with it. So let me give you a ranking task because we love them, don't we? Yeah. The enthusiasm was not there. Let's try that again. We're going to do a ranking task because we love them, right?
Yeah.
Awesome. All right. I love that. All right, here we go. So you can hold on to that. Yeah, I'll get them out so you can answer it then. Keep keep that pink sheet out because we're going to use it. We're going to refer to it. The pink sheet was not just, let's just fill it out to waste time. I don't do that. Like that, no, that wastes paper and time. Take a look at this question. Use your pink sheet as a resource. Shown below are 6 velocity time graphs. So Isaac is not going to get tripped up by this. It's a velocity time graph, right? Not a displacement time graph. For toy robots, they're traveling along a straight hallway. I love that like image. All the graphs have the same velocity scale. So it's all the same, like one box is 1 meter per second, let's say. It says rank the magnitude of the acceleration during those time intervals. I want you to work by yourself for just a moment. This is you and your brain. You can just write down a little note to yourself. See if you can figure it out. I will get whiteboards out so we can do that in just a sec, but I want you to see if you can figure it out first on your own. Again, use that pink sheet. That's what it's there for. So write something down, some guess or some idea of what the answer might be. Not saying it has to be right? We're learning together. We make mistakes together, and that's cool. All right, have a conversation at your table. Come up with an answer, write it on the whiteboard.
The acceleration is not equal.
Did I give everybody a marker? Or you can just copy it.
It's the absolute sum, but actually, so I think it's A and D are zeros. So A is equal to D.
We know that.
All right. See if you can come up with an answer. Again, you guys, this is why we do this, right? It's to learn and to think. Give me something to work with.
So that's why all of you in the stream, have 4 answers.
So E is. Okay, so it's 2.
So,
Yeah, B and C.
Excuse me.
I know. E is greater. E, which is equal to C. Yeah, you're right.
So it's
it's very similar to if you had a displacement graph,
If you give just
and
one
only for the velocity.
acceleration to this acceleration.
No, A is
Easy.
yeah.
No B.
But if the magnitude.
So the values don't matter. But if the slope is negative, than the value of acceleration.
Yeah.
Do you remember we had that big fight about like speed versus velocity earlier? Yeah. So acceleration.
It's a negative.
Oh, and that
You're
just.
pulling down.
It's a negative acceleration.
You accelerate per second.
Give me no. Wrong. Put something down. All right. All right. Let me see your boards, friends. Let me see where we're at. I'm gonna make this a little smaller. We may have a bunch of different answers because that's we're still learning. So put them up. Hold them up so I can see them, so I can write some answers down here. So I see C equals E greater than F greater than A equals D greater than B. Okay, got that one. E greater than B equals C greater than F greater than A equals D. All right, let me see here. We've got F equals E. You guys coming up with an answer? Because I'm okay. You have a good. I just want to see it. Hold on. C. No, it's okay. There's no names associated with any of this, right? No names associated. We've got 4 different answers maybe, which is awesome because that means learning is going to happen. B greater than A equals C. Did you draw? Oh, I thought that was a robot. That is not a robot. All right. Mira, what? I don't want to see the question mark. I just want to see your answer. Nope. A, B, C, D, F. Gotcha. You're awesome. Okay. So here we go, friends. We got to figure this out. I've got 5 tables and 5 answers. Help me out. What do we got? What do we know? Where did your brain start with this concept, this process? Go.
You know that magnitude is absolute value.
Okay, so, okay, I'm sorry.
So negatives go.
Okay, did you all hear that? Are y'all listening? Make sure you hear that. What are we talking about? We said that the what? It said, what does it say? That key word that Stella just pointed out to us? Magnitude. So what does that mean?
Absolute value.
Means absolute value. So it means that negatives don't matter, right? I was just talking to Emma about that, right? Because it's like negatives, do they matter? Do they matter? In this case, because it says magnitude, the negatives do not matter. Good to know. Good to know. Okay. So we know that. What else do we know? What else can we figure out? Let's look at the easy ones first. I like the way you think.
Let's do the ones that are slope of 0.
Okay, let's do that, and then I'm going to come back to you. Is that okay? So which ones have a slope of 0? A and D both have a slope of 0. So that's going to be easy because that means acceleration is 0. Do you guys understand why we said that? Yeah? So that would be like on the pink sheet. Where does that one exist? Slope equals 0 for the velocity that's here, right? If the slope equals 0, that means the acceleration is 0. Boom, we're done. Sweet. Okay. Let's go to the next thing. So now we've got 4 other ones. What are we going to do next? Ben, you had your hand up. You were going to talk.
Oh, I was going to talk about A and B.
Oh, is that what you were going to say? So you just stole your thunder there?
Yeah.
Jeez. Go ahead.
B and C are equal
How do you know B and C are equal?
because their slope is the same.
Okay, that's cool. I just wanted you to say that. I'm not like, what are you talking about? Yes, they are. They're the slope. They're the magnitude of their slope is the same, right?
Yes.
One of them's positive, one of them's negative. You guys with me back there? Everybody's good? I want to make sure because this is not trivial stuff. This is important. Yeah, so it goes like 1, 2, 3, 4, 5 over and 1.5. Yeah, so B has to equal C. I think we know that. B has to equal C. We know that A has to equal D. So these guys are, what did I just say? It was like 1.5 over 4. Oh, that's kind of a gross thing. Whatever, it doesn't matter that much. All right, help me out with E and F.
Wait, is it 5?
Is it 5? Did I count wrong?
Yeah.
It is 5. 1.5 over 5. That's even more or something. I guess it doesn't matter. All right. Help me out with E and F.
You gotta see which one's greater.
Let's see which one's greater. So F has a rise of 1 over 5. So this one is 1 over 5. And this one is what? Up 2 over 5? Okay, so if we write this out, now it's not too bad. We're just looking at fractions. And have I told you guys that I have this dream of someday dressing up as a fraction for Halloween? Because you always want to dress up as things that are scary, and I feel like a lot of times students get like really scared of fractions. So I'm like, I still haven't figured out how I'm going to do it, because I think it would be awesome and hilarious, and maybe I'd be the only one that thought it was funny, but I would think it was hilarious. Anyway, okay. Yeah? Do you get it? I think it's funny. Anyway, so we're not going to be scared of fractions because all we need to do is look at the numerator. So 0 is the smallest. Do you guys agree? Yeah. So A and D are equal? Oh, thanks for catching me. True there. A and D are the same. And they are the smallest. Thank you. All right. Which one of these is the biggest? E, because it's 2/5, right? Yeah. And then what's bigger? Or then what's next? Then what's next?
We got our B and C.
B and C are next?
Yes.
Boom. And then what? We get that? Anybody got that? Yeah. Nice job, whoever that was. I don't know. I don't keep. Apparently, they're claiming it. Anybody can claim it because I don't have names on it. So yeah. Yay, 13. All right. This was kind of tough, especially as like a first round in there. But do you understand where this is coming from?
Yes.
So in your notes by this, you could just make yourself a note. Just remind yourself that if you're looking for the acceleration, the value of the acceleration, what do you look at in the velocity versus time graph? Say it loud and proud.
Slow.
There you go. Yeah. Okay. I wanted to throw one more in there, but I want to make sure that we get a chance to go over some homework. So I want to do that first. Is that okay? Because we have not gone over the homework from way back. Is that true? Yeah? Okay. So put the cap on your marker, leave it there, because we may have time to go over to do one more ranking test. I know you would be eager to do that, but I'm not positive we'll have time. So plug your homework. You might want to keep that pink sheet out because we're going to refer to it. We need it. We need it. We need it. We need to go over, let's see, what were those problems? Really, I want to look first at, why is this not working? Come on, thing. I want to look at these guys, the 5, 6. So page 57, 5 and 6, and 73, 1 through 4. Were there any of those ones that you guys wanted to go over? They were all really hard? Okay, so my guess is that now after the conversation today, they're not going to be quite so hard. So let's take a look at them. If you would like to, and by that I mean I would encourage you to go grab a book real quick. Just one per pair if you don't have one out in front of you. I'm going to start on page 57. I'm going to try out this thing so that I don't have to draw this graph. We'll see if this works or not. Come on, team. Hey, look at that graph. All right. So let's take a look at this. My guess is that now that we've had the conversations we've had in the last couple of days, this should be better than maybe it was when you first looked at it, but let's just check. So this is number 5 on page something. 57, thank you. The velocity versus time graph for a shuttle bus moving along a straight path is shown. Identify the time intervals during which the velocity is constant. Again, it's a velocity versus time graph. When is the velocity constant? What's that? What am I looking for? Maybe that's my question. What's that? When it's a straight line. This is a straight line, is that right?
Well, no, I mean zero slope.
There you go. So right here?
Yes.
Yeah? Right here?
Yes.
Yeah, those would be your times. Is that okay?
Then you
For A? Identify it, yeah, so like what is that? Like 50 to 150 and 200 to 275 or something like that?
There's 1, 0 to.
Oh, yeah. And 0 to whatever, 25 or something like that. Yeah. Yeah, good call. Good call. Yes, I didn't even catch that. Thank you. How are we doing? Are we okay so far?
Yeah.
Okay, part B. Identify the time intervals during which the acceleration. We can do this now, right? Because we understand this. It says the acceleration of the shuttle bus is constant. Okay, let's think back or look at our pink sheet. If the acceleration is constant, what are we looking for in a velocity graph? What'd you say? Like not a curve, right? Yeah, so the acceleration is constant. So, I don't actually know what the answer is written down for this one, but here, let me just look here. So they say 0 to 30, 30 to 60, 60 to 125, 125 to 210. They list every single piece. Does that make sense to you? The time intervals, is the acceleration constant here? Yeah, because it's not moving. Is the acceleration constant here?
Yes.
Yeah. It's got some value. We could find it if we wanted to. We just find the slope, right? Is that making sense? Is it constant here? Yeah. The only time when the acceleration wouldn't be constant is if the slope wasn't constant. Yeah, so that might be something to write down if you want to just like make a note by that, right? As long as you've got straight lines, you've got constant acceleration. So that's cool. Part C, find the value for the average velocity of the shuttle bus during each time interval. Well, that's going to be obnoxious. The value of the average velocity. So let's just talk about how one might do that. That sound okay? So average velocity. What's the average velocity in this little time interval?
0.
That one's easy. The average velocity in this time interval? Well, it's going to be 30. Well, yeah, so like it's going to be like half of that, right? So like 15, right? Does that make sense? The average velocity is just going to be in the middle? Is that okay? The average velocity over this time, well, if it's only 30, the average is going to be, it's like it's 30 here, and it's 30 here, and it's 30 here, and it's 30 here. If I'm going to take an average of all those 30s, what's it going to be? 30. You okay there? Yeah, this is not as hard as I thought it was going to be. If I've got from 30 to 0, what's the average of 30 to 0? 15. Yeah. Oh, are they all points?
Yeah.
Oh, silly decimals that I can barely see. Thanks for calling me on that. Can you see that? It's like kind of hard to see. You're right, though.
Yeah.
Yeah.
I didn't want to
Move my always say something. Always say something. Do you know, it was last Friday, it was a week ago. I don't know if you remember, I was feeling really icky. And I was like, ugh. We were going through the quiz. I went through like an entire problem that was not the right problem. Nobody said anything until the end. Oh my gosh. Always tell your teacher if you're confused, please. Like it's so much better and it wastes much less time. Okay, so thank you for telling me. Always tell me. Okay, that was C. Do you get the idea?
Yes.
Questions there? Josie, how you doing? Yeah. You sure?
Yeah.
Okay, ask me questions if you have them. Find the acceleration of the shuttle bus during each of the time intervals. How would you do that? How do you find the acceleration? Say it loud and proud. The slope. Right? So you just find the slope here and the slope here. Can you do that? Yeah? Okay. I'm not going to go through it because I'm just trying to move fast, but is this okay? Yeah. I did put the values of all of this stuff up on Canvas. So if you want to check your numbers, please feel free to do that. This one is kind of hard to read, so I'm not going to get like all meh if it isn't quite perfect, but you get the idea. The process is what's important. What was that? That was D. Identify the times at which the instantaneous velocity is 0. When does that happen? Where would we be looking for on the graph?
The lines on the x-axis.
Line on the x-axis. Boom, boom. Okay, we're not moving anywhere. So this is like bus stop 1, bus stop 2. Seems to me. Boom, boom, boom. F. Identify the times when the acceleration is 0. How do you know when the acceleration is 0? What's that? The top one right here? How about here? And how about here?
Oh, yeah.
Yeah. As long as the slope is 0, the acceleration is 0. Is this making sense? Like, is this all kind of like fitting together? This was totally hard before we had gone through this, right? You kind of like let it simmer in your brain a little bit. So I hope that that's like been a positive thing. All right. So that was E. F. Identify the times. I did that one already, right? G. Explain what the slope of the graph reveals. What's the slope of each part of the graph reveal? What does it tell you? Slowing down? Or it's speeding up, right? The slope is just going to tell you what the acceleration is. So yes, it would be slowing down or it would be speeding up depending on which kind we're talking about. How are we doing? Is that okay? Make sense? Question 6. Is the shuttle bus in item 5 always moving in the same direction?
That's item 5.
Well, this is item 5. So look at this graph. That's what they're saying. Is it moving in the same direction? Why do you say no?
It was past the point that it started.
Okay. We have to be careful. Yeah, like I totally, yeah, we're looking for.
It was like, so it went past 0 and then below something, so it's basically past the point that it was at.
Yeah. I agree with you almost. I was like, yeah, because I was, no, you were totally right. Do you remember we were doing those displacement versus time graphs? Right? So I did that walking and then I walked back here and then I walked way back here and that's when it crossed the axis and that's what you're thinking of, right? Yeah, but that was a displacement graph. Are you with me there? Yeah. Now this one, unfortunately, but we've been catching ourselves all day, is a velocity graph. Does that difference make sense? So I totally agree. If this was a displacement graph, boom, you're done. You got it. But here we have to think a little bit harder. So this is, I'm not moving. And now here, what am I doing? I'm moving in the positive direction. Okay? And then here I'm moving in the positive direction that way. Are you with me there? Now what happens here? I'm slowing down, slowing down, slowing down, slowing down, slowing down, slowing down. Stopped? Yeah? And what's happening here now? I'm going, what'd you say? Yeah, so that means I'm going backwards. Yeah, the negative just means I'm going backwards. Is that what that said? Yeah, it did. Yeah. What was I thinking about? Oh, I was thinking about going like behind there. You're right. I'm sorry. I was answering a different question. No, you are fine. Let me explain, because this was me. No. Come here. Look at me, because I need to tell you. No. Stop laughing at me. You're laughing at me. Okay, so can I tell you? I'm gonna let you laugh for a second. I'm gonna move to the next page, so I'm gonna tell you what I was gonna tell you. Because it's totally it's a carbling issue. Oh, friend, are you okay? Did I totally ruin your day? What just happened?
I slapped you.
Me or her?
Josie. No, you're fine. I'm not gonna slap you.
I figured not. Let me tell you what happened, Mira. I thought you were answering a different question than you actually were. You were totally right. I was wrong. I was anticipating. This is what happens as a teacher sometimes. Like you think, oh, they're going to answer this way. It happens all the time to me, so I apologize. You were totally right. I apologize. My bad. Happens. All right. We've got, what, 2 minutes? Go. Did number 1 go okay? From the other page? On the graph below, because we did that, right? Number 1? 1 through 4?
Yeah.
On the graph below, what is the total distance traveled during the recorded time?
6 meters.
6 meters. 6 meters?
5.
Who said 5? Why 5?
Because we didn't start at 0.
6 minus 1.
Boom. There you go.
6 minus 1.
All right. Let's do one more. Number 2. What represents the instantaneous velocity? It's a displacement versus time graph this time.
What does instantaneous mean?
Instantaneous right now. Boom.
Okay.
Right? So like if you're driving in a car, your speedometer
Yes.
is your instantaneous velocity. It doesn't take into account any stops and starts. Does that make sense?
Yes.
Sweet. How do you find the velocity of a position versus time graph, guys? Look at your red sheet if you need to.
Position medical.
I want to find velocity. I've got a position versus time graph. What do I look at? The what?
The position or distance over time.
It does, but this is ugly. This is curvy.
Oh, yeah.
How can I find the velocity at any given point? You can't. We just go home and cry.
Can you do that tangent thing?
Yeah, you totally do that tangent thingy. So you're just gonna look at this. You're just gonna look at the slope. Yep. You're just gonna look at the slope. So you're not gonna have to actually calculate it, but you need to know that idea. All right, ladies and gentlemen, thank you so